This presentation is on developing services, modeling in the XOS Toolchain. My name is Scott Baker, and I'm with opennetworking.org. Sapin is also a person you might want to contact for modeling, so either one of us, if you have modeling questions, we can usually field them. So the goals of this talk, we wanted to look at some questions that a person might ask. So one of them is, I'm a VNF developer. What do I need to know to integrate my VNF with Chord? How does my VNF learn about other VNFs? How do they learn about my VNF? How can I make use of XOS's generative toolchain to reduce the amount of manual coding that I need to do? And of course, what opportunities are there for me to contribute back to the Chord community useful features that Chord services and other developers can use? So we're going to start by talking about modeling and why is modeling important. The design of Chord, XOS in particular, is driven by the data model. Modeling is how you make your service available to a Chord pod. Modeling is how services learn about each other. Modeling is how your service exposes configuration to the operator. So for example, if you want settings that the operator can change so that those settings would be realized in your service and reconfigure your VNF, that's how you do it, is through modeling. And modeling is how your service learns about resources that are available on the pod. So for example, how it learns about compute nodes. This talk is going to show you how to model your service and introduce you to some of the tools in XOS that interact with models. So some basics about how XOS is designed. The XOS data model is centralized. We have a container called the XOS core container. That container, we like to think of it as providing data model as a service. It's going to handle all of your data model tasks for you and serve it up via gRPC API. So you would submit your data model specification to the core, and the core is going to handle setting up a database like MySQL or Postgres. You really don't need to know how the core does its job, just that it provides this service for you. The data model is extensible, so services can register their own models. Those models will be available for your use as well as for other services to use those models. The data model is relational. We like to design the system so that data is stored only once and then linked as appropriate. That avoids various consistency problems. So for example, in our Chord, we have the VSG and VOLT services. The VOLT service knows your S tag and C tag. Rather than duplicating that information in the VSG service, we just have a link from VSG to VOLT. Relational databases provide several integrity and constraint features. One of those is entity integrity that ensures that there are no duplicates in the database. You can designate fields in your model that are keys, and the database system will not allow you to put in two records with the same keys that would conflict. There's also domain integrity, which is restrictions on the type, format, or range of values. So you could say, for example, that a string could only have certain values associated with it. And most important for the core container is this referential integrity, which is the data in use cannot be deleted. So if you have a relation from one object to another, you cannot delete one of those objects and cause the database to get in an inconsistent state where there's a dangling pointer. It just won't let you do that. You either have to delete those things at the same time, or you have to clean up the pointer before you can delete it. So some of the constructs that we have in the XOS data model. So models are the key thing, and a model is a description of a data structure. You can think of like a C struct as a form of a model in that it defines, for this data structure, what are the members of it. Models are instantiated as objects, so you go from a description of the data format to actually the data values stored in the database. And a primary key uniquely identifies each object, so we always have some handle that we can use to retrieve the data at a later time. And these translate directly into database concepts. So models are database tables, objects are rows in tables, etc. Models have various fields. There's simple fields, integers, floating point values, text strings, booleans. There's also this foreign key, and that is how we do relations. So foreign keys go from one object to another, and they're actually typed. So you can't just have a foreign key go from one model to just any random model. Your model will often say, for example, if you have a slice model, it can be linked to a site. You can't just link it to anything else. It has to link to a site. So they're typed like that. The third kind of field we have is computed fields. They are typically generated by using a query. And one example of this is reverse references for foreign keys. So let's say we have a foreign key from a slice to a site. You automatically get the reverse reference for free. So your site would automatically come with a list of slices. So that means that any foreign key is essentially bidirectional. You can go from model A to B, and then from B back to A. We divide the fields in our models into two different kinds of members, declarative and feedback. So declarative state is generally specified by the operator in some manner. It can be traced back to, for example, a Tosca recipe or something somebody clicked in the GUI, something like that. It's state that you wanted to put the system into. Some examples of declarative state, for example, a username or an email address for a user record. You know, you type that in, that's the state you wanted it to be. Our subscriber objects have a bandwidth limit. You know, someone would have specified that bandwidth limit. Even something as complex as a network topology, someone, you know, sat down and figured out how those networks are supposed to be plumbed together. Declarative state is generally pushed from XOS to components. So, for example, from XOS to OpenStack in order to configure those components. In the opposite direction, you have feedback state. And feedback state is status information or identity information that flows from the components back up into XOS. The most common form of feedback is just did an operation succeed? So an operation it either succeeded or it failed. And then if it did fail, was there an error associated with it? So for example, you create something in OpenStack, it fails. That failure as well as the error code gets pushed back to XOS. If something succeeds, oftentimes there's a component-specific identifier that will come with it. So let's say you created an instance and it succeeded, then you would get back an instance ID. And this state is pulled from components into XOS. Now I have a picture of this which basically illustrates what I just said. Say we have the instance model in XOS. There will be a corresponding instance in OpenStack. Those constructs kind of mirror one another. And your declarative state would be, you know, that you want your instance to have 4 cores and you want it to be located on node 7. So that would get pushed from XOS to OpenStack, and then there would be some feedback state that would come back and say, okay, I succeeded, I made your instance, and I assigned it instance ID 7. That is an example of declarative and feedback state. This will become more apparent and more useful, I think, during tomorrow's discussion of the synchronizer, where we will talk about how the specific data flows work in the synchronizer. So now we're going to talk about how you would model your service. This is under the assumption that most people here are going to be interested in developing services. So we want to introduce you to the types of models that go into a service. There's three primary kinds of models. The first is the service model, and that would have service-wide global parameters. So consider, for example, the virtual subscriber gateway, the VSG. One thing that we might have in the VSG service is a DNS server that you want all of your VSGs to contact that particular DNS server. That would be an example of global service-wide state because it's something that you want spread across the entire service. Now, the service instance models, that is how we divide a tenant, or how we divide a service into tenant-sized pieces. And we have this term that we've used in the past called unit of tenancy. And it may be different depending on your service, how you partition it up. This is how you make a multi-tenant service. So for example, a lot of our services are divided up by subscriber. The VSG is one example of a service like that, in that each subscriber typically gets his own personal VSG running on Cord. ONOS is another example of a multi-tenant service, but its tenancy is divided up in an entirely different way. We have ONOS as a service, but it's divided up into apps. So each entity that wants to use ONOS typically runs an app on ONOS. And a third example is a CDN. The CDN will divide up by content provider. Different providers will want to make different content available on the CDN. So when they go to register themselves with the CDN, they will get a content provider chunk of the CDN. It's also important to note that not all services are multi-tenant. For example, we have the VTN service, that it has global state, but it really doesn't create any specific tenant-sized chunks. It just kind of pulls its information from other components in XOS. So there's also some auxiliary models, and auxiliary models would be anything that doesn't fit in the service model or the service instance model. And this will come into play when you want your service instance to be able to dynamically grow. And an example of this that we ran into is we modeled our Cord subscribers one time for a demo, and we wanted to be able to model various computers at the subscriber's house, so like mom's PC and dad's PC. And you don't want to just create a fixed amount of them, like say we could only hold 4 of them. You want to be able to have a variable list. So you'd create an additional model called, subscriber's computer, and then you could create as many of those as you want and link them to your service instance. And we're going to go through a functional example of all of these models in a couple slides. Here's a picture just to illustrate how the RCord models are laid out. So you see in the blue boxes are services. So we have like the RCord service, the Volt service, VSG address manager. And each one of these services can have many service instances. So the Volt service, it could have, Volt service instance number 6, and there could also be a number 5 and a number 4. There could conceivably be hundreds or thousands, or depending on how we scale, even millions of these things. Because this is how you partition your service up in a multi-tenant way. So may not be easy to see the colors, but the vertical lines are red, and those represent ownership. So each service instance is always owned by a service. And then we have various graphs going horizontally. So there's a dependency graph and a link graph. And I'm going to discuss those graphs, I think, on the next page. So connecting services together. Services are often related to other services. For example, we've been talking about the VSG, and the VSG will usually have both an ingress and an egress, so a way of getting traffic from the subscriber into the VSG and a way of getting traffic out of the VSG onto the internet. The ingress service would typically be something like VoLT, the egress something like vRouter or Address Manager. So XOS does include modeling support for these service graphs. You don't have to implement these linkage models yourself. They're already part of the data model. So you don't need to create these, but you should be aware of how they're used by XOS to connect services together. So I'm going to show several examples of these various graphs. So XOS implements 2 types of graphs, and that's not surprising because we have 2 types of service models. We had the service model itself, and then we had the service instance model. So there'll be an associated graph with each one of those. For the service models, we have the service dependency graph. And the service dependency graph, it represents high-level dependencies or requirements between services. So for example, such a dependency might be that the VTN service depends on ONOS. And the reason for that is that VTN runs in an ONOS app on ONOS. So you cannot bring up a pod and use VTN unless your pod has ONOS. So there is a hard dependency there. Is also another dependency would be VSG depends on address manager. And the reason for that is a VSG, its purpose is to put subscriber traffic out on the internet, so it needs a public address. And the place you get those public addresses from is the address manager service. So you create these dependencies in the data model to reference those sorts of requirements. We worked hard to try to eliminate hard coding these dependencies so that, for example, if you had something else that was able to provide addresses, you could substitute it for the address manager service. You shouldn't think of these as it must be this way, although in some cases like ONOS, there's really not something else that provides an ONOS. We've only got one of those in this world. Service dependency graphs don't necessarily imply connectivity. For example, there's no connectivity between VTN and ONOS. They're just sort of components in the system. They just require one another. But sometimes they do, and we'll get into that in a moment. The service dependency graph, you could represent it as a directed acyclical graph. I don't think it really makes sense to have cycles in it because one thing shouldn't require another that goes back and requires it. So we postulated that it's probably acyclical. And this is implemented through a model called the service dependency model. And it's a pretty simple model where it has a subscriber service, a provider service, and a connection method. The connection method is a hint to XOS to tell it how you might want your service instances wired together. Does your service connect to things over the data plane, the control plane, or does it have no actual connection between these things? Here's an example of a service dependency graph. This example comes from RCord. So what we have in there is we have ONOS, and a lot of things use ONOS. So the VTN service uses ONOS, VOLT uses ONOS, and vRouter uses ONOS. You can also see the VSG services in there. So VOLT is using VSG, VSG is using vRouter, VSG is also using address manager. So as you add new services, you can incorporate them into the graph and map out the dependencies between them. The other type of graph we have is the service instance graph. The service instance graph expresses connections between service instances. Now this often does imply data plane connectivity in that a lot of things on the service instance graph are service instances that do end up on the data plane. So things like Volt service instances and VSG service instances and public addresses. We have a lot of flexibility that we built into the data model. That is something that was one of our primary goals of the 4.0 release, was to add this flexibility in that we can model not just chains like we typically talk about, but also we can model trees, directed acyclical graphs, or even hypothetically cyclical graphs if you had something that actually needed a cycle in it. I'm going to have some examples of all of those. And this is implemented through a model called the service instance link model. A service instance link goes from a subscriber service instance to a provider service instance. So let's take a look at a simple chain of services. So this is right out of RCord. And this is the chain you would have for a typical RCord subscriber. So here we have, all of these are numbered because each service instance has a unique ID. So for example, subscriber 10, perhaps it is subscribed to VOLT 6. And then VOLT 6 has a link to VSG number 24. And then VSG 24, maybe it uses public address number 11. The boxes are all service instances. The arrows are all service instance link models. But one of the things we'd like to do is to get people to invent more interesting service graphs than just the chains. And that's one of the reasons why we baked in the ability to have some of these additional forks and joins. So let's say you wanted to add a fork to your service chain. And what I've done is I've added this classifier. So this is hypothetical. I don't think we actually have a service that does this at this point, but let's assume we had a classification service that was able to classify packets into either a fast path or a slow path. So we've added classifier number 4 in there, and it could send traffic either out to fast path number 13 or back down to VSG 27. And let's assume the fast path is something that's implemented entirely in ONOS, so it could go through your switch without ever having to touch a compute node. But these are also linked back to the same public address because the subscriber wanted to get out on the public internet. So this chain illustrates both a fork and a join. And we'd really like people to try to come up with some stuff like this, contribute it back to the community, give us some unique service graphs like this, come up with some use cases. Another hypothetical is that we could have a cycle in the graph. So let's assume we added a CDN. We stuck the CDN down there at the bottom, and traffic goes into the VSG, and the VSG says, this traffic, I think I can serve it locally in my cache. So it sends that traffic down to the CDN. And just hypothetically, again, we haven't actually implemented this, but hypothetically, let's say the CDN had a fast path where it could send the traffic, it could send a reply directly back to the subscriber without having to send it back through the VSG or through the classifier. We can model that in the service graph. We just need someone to implement these VNFs that would allow us to do these unique things. So I've given kind of an overview of the types of models that comprise a service. Next, I want to kind of transition the talk from the abstract to a little bit more concrete, walk through an example of a service, dive into the specification language that we have. It's called ExProto. And the key point here that we have, and I think we've made it in a few of the other talks, is that there's a lot of moving parts that comprise a service. So you might have a GUI, you might have a Tosca API, maybe you also have a security framework, you have its data model presence. Life would be easier for all developers if we could just auto-generate all of those things from that single specification. So why does that make a developer's life easier? Well, you're going to make fewer mistakes if you have less to do, less repetition, so less of this just copy-paste coding from one place to another, quicker implementation. It's more maintainable because if you want to make a high-level change, just make the change at the high level, will auto-generate all of the low-level details. And the basic, what it boils down to is that more time that you can spend on the interesting parts of your service and less time spent doing the less interesting migration or integration aspects of your service. So to support this, we developed our own language called the ExProto language. That is a modeling language. The expert on this is Sapin, who is in the audience. And when we sat down and we wanted to figure out how to do this, we realized we had some requirements. The requirements are that we need, first of all, we needed something to describe data structures. So for a given model, what fields go into it, and integers, strings, et cetera. But we also had these more modeling-related requirements. For example, we have to be able to specify relations between models. That's something that not all data structure specification languages support. We wanted to be able to leverage this specification language to support security policies and to support validation policies and inheritance from one model to another, so you don't have to do that copy and paste coding so that you get kind of reuse inherently. So what we did is we couldn't find exactly what we wanted out there, so we thought we'd base something off of Google protobuf, since protobuf seemed a convenient syntax for us, and protobuf has wide adoption and wide support. So what we did is we started off with the protobuf message as the basis for our XOS data model specification. And we added some additional syntax so that our syntax is very much like protobuf, but has this additional sugaring to allow you to express more stuff. And at the same time, we kept this so there's a one-to-one correspondence between our sugared syntax and plain ordinary protobuf with ordinary protobuf options. So you can always convert between one or the other. And we wrote a tool called XOS Gen X that is the ExProto translator that will translate ExProto specifications into various useful outputs. So XOS Gen X, it takes ExProto as its input together with a Jinja 2 template we call an X target, and it produces an output. Because Jinja 2 is a templating language, it's general purpose, and XOS Gen X is inherently extensible to new use cases. If you want to have support for new output, you just write a new Jinja 2 X target file. And you can do that for as many things as you can imagine, possibly auto-generating. XOS Gen X, it's automatically invoked by other tools. I think during the build system discussion, there was probably mention of the Core Builder tool. And Core Builder is one place where we invoke ExProto automatically. So often, a service developer won't even have to interact with XOS Gen X himself, but you need to be aware it's there in case you do want to experiment with it, or in case you run into problems, or in case you just want to know how things work. So down here is a graphical example. We have a slice.exproto. That is the ExProto definition of the slice object in XOS. We convert that to an intermediate representation internally, and then we apply it to an X target called Django.xtarget. That is an X target that we wrote to generate Django data model Python code, making use of some library functions. We generate slice.py, and slice.py is the Django model that would go into the XOS core container to bring up slices in the XOS core. So what types of things can we auto-generate? XOS Gen X has many existing targets already. So we can generate the database schema. That was the example I just showed where we generated the Django Python file. We can generate a gRPC API. That gRPC API is then made into a REST API via Chameleon. We can auto-generate a Tosca schema in our new Tosca engine. We can auto-generate a graphical user interface, synchronizer stubs, documentation like Swagger documentation for the APIs, a security framework, and there's many more. If you look at the slides later, you'll find this URL down there which will point you directly to the GitHub repo where all the X targets are located, and you can see the variety of X targets that are available. So just looking at one of these X target files, this one is dot.xtarget, and it makes model graphs for the dot tool. And I'm not going to go into detail on all of the syntax, but you can kind of see that it has some constructs in here for a for loop that's looping over the various models that are in the data model, and then another for loop that's looping over the links in those data models, and then something that's printing out pairs of model name and peer name. And you can imagine this generates a large graph file that you could visualize in a graph tool that would show you how models link together. That's just an example of an X target file. There's many other X target files that you can look through. So let's take a closer look at the ExProto language. To do that, I'm going to walk through an example. We call this example service. This is a service that brings up web servers. So what the unit of tenancy is going to be is an individual web server. So you can think of this as kind of like the web server service you'd go to if you wanted a web server brought up for you. This is an entirely toy example, just made to illustrate modeling and synchronizers and such in XOS. It's not particularly practical. There would be more practical ways of generating web servers probably than this. So we'll have some kind of toy message strings that we'll put in there to illustrate how it works. So we're going to assume people want to have one service-wide message string that will be present in all web servers. And that will be going into the service model. And then for the service instance model, we're going to give you a tenant-specific message string, which is a different string that you could put into each individual server. So then when we bring up a web server, we will give you a web page that puts those two strings together. We're also at the service instance level going to let you specify some colors for your page and add some embedded images to your page. So I sketched out kind of a picture of what these models might look for in a service that you deployed. So there's the example service, and maybe we set the message string in it to hello. Then we created an example service instance, and we set its message string to world. Concatenate those together, obviously you get hello world. Then we had some other models for representing colors and some foreign keys for foreground and background colors from the service instance to those color objects. And then we have some embedded images. In this case, I put in 3 embedded images, and each one of those has a foreign key going back to the service instance. And this allows you to have a service instance with a couple colors, a message, 3 images. Just a toy example to illustrate some modeling. Let's take a look at the ExProto. This is the ExProto for the example service model. We've syntax highlighted it. It is, as I said, it's a derivative of protobuf syntax. So you see this word message starts off every model. And then we have the model name, which is example service. And then we have inheritance. So inside the parentheses is the model we want to inherit from. In this case, we wanted example service to inherit all of the fields from service. And down here at the bottom, I included a little snippet of what the service model looks like in the XOS core. So you don't need to know much about service for the purposes of this talk, other than there's a whole bunch of fields inside service, things like description and enabled, service name, service version. There's a dozen or so fields down there in service. So we've inherited service into example service, then we have an option. The option is a verbose name. That's something we use in the GUI to present human readable names. Then we have the first field in our example service object, and it is a required string field called service message. That's the one that I said maybe we'd set to hello in the previous screen. So service message, it's assigned a number 1. The number is something that comes from protobuf. Each field in protobuf needs to be assigned a unique number so they can be disambiguated at a later date. Inside of the square brackets, we have some options. So there is some help text. Help text is set to service message to display. That's something we would put in the GUI to help the user of the GUI know what this field is for. We've got a maximum length, whether or not you can set this field to null. Null is a slightly different thing than the empty string from a database perspective. So you might run into that implementation detail at some time. That's why there's both a null and a blank. So blank sets whether the GUI and the Tosca engine, I believe, will allow you to set the field to an empty value. DB index is whether or not this field will be indexed by the database. And that is the service object. So the next model we have is the color model. And this is same syntax as before. So we've got message. The name of the model is color. It's going to inherit from a different model. It's going to inherit from the XOS base model instead of from the service model. XOS base is sort of our most basic model in XOS and includes lots of internal bookkeeping stuff. We have, again, an option for the verbose name. We have a couple of strings, one for the name of the color object and one for an HTML code that'll go with it. So the name will be something human readable like red, whereas the HTML code will be some HTML page construct like FF0000, perhaps for the red color. So the next model in our example service is going to be example service instance. Again, it starts with message. It has the name of the model, example service instance. This time we're going to inherit from tenant with container. Now, tenant with container has a whole bunch of functionality that comes with it. It automatically is smart enough to generate an OpenStack instance that goes along with this service instance in order to implement your VNF. And it's somewhat beyond the scope of this talk to explain all of the things that tenant with container will do for you. Just know that it is a model that you can inherit from in XOS. Many services do inherit it because it gives you all of those features for automatically creating instances. Again, we have a verbose name for human readability. We have a string, which is going to hold our tenant message. But now we have two new fields down here that we haven't seen before. These are foreign keys. They're many-to-one relations. They're optional, meaning you can set them to none. You can leave them out. And down here, this is where we've extended some of the syntax of protobuf. So you have the name of the field is foreground color. It points to a color model. Color was the model I just showed on the previous slide. And over here, we want to automatically create a reverse foreign key called service instance underscore foreground underscore colors. So what we'll get is one field in the example service instance model called foreground color, and then another field will show up in the color model automatically called service instance underscore foreground underscore colors. We have set this to null equals true and blank equals true because we want you to be able to leave that null if you want. If you don't specify a color, we'll pick a default. We do the same thing with the background color. Give it a unique field name, background color, points to the color model. And like before, we've given it a back reference. Now, the back reference has to be different for each one because we're going to create a field in the color model, in this case called service instance background colors, that will contain a list of all of the example service instances that were linked to that color. My laptop's getting a little bit slow here for some reason. So the final model is the embedded image model. Embedded image is what we're going to use to hold embedded images that would go along with the sample web page we're going to deploy inside of the example service. So again, it's inheriting from XOS base. It's got a verbose name for human readability in the GUI. It's got a couple of string fields. One of them will be the name of the image. The other string field will be the URL for the image. And then we have a foreign key down here, which is a many-to-one from service. We're going to call the field service instance. It's going to point back to example service instance, the model I just showed you. And in example service instance, it will create a reverse field called embedded images. Now you've noticed that I did the foreign keys slightly differently for color and for image. That was on purpose. So back here in the service instance, we had foreign keys that pointed to colors. That's because each service instance we've set it up can have exactly one foreground color and one background color. But we wanted to, for the purposes of this example, to have it so that you could have multiple embedded images associated with one service instance. So we put the relation in the embedded image model instead. That way you could create as many embedded images as you want, foreign key link them back to your service instance, and your service instance automatically gets that field called embedded images, which will contain a list of these. So we also have a policy framework that goes along with ExProto. The policy framework uses limited logic expressions. They're limited in the sense that I think they have to terminate, they can't cycle. The logic expressions have two inputs. One of the inputs is a security context, which is sort of everything we know about the current user and the API that he's calling with. So, you know, is his user ID, as well as is he a synchronizer that's calling in, or is he an actual GUI user, et cetera. And it has the entire data model available as input to one of these logic expressions. And the output of this logic expression is either true or false. And for example, we'd use that in the security framework. You know, true means you can do something, false means you can't. We compile these policies into Python. And this is actually something that we designed to be general purpose. So while we use it inside of XOS to implement our security and validation frameworks, you could also leverage this outside of XOS. And that's one of the things that we would like to see the community try to develop more, is to come up with ways for us to use this policy framework, maybe even inside of VNFs. And I will have some thoughts on that at the very end of the presentation. I'm not going to go deeply into the syntax on these ExProto policies. I just wanted to illustrate a couple of them. So I've put in a couple of validation policies. They start out with a policy keyword, then we give them a name, and then inside of the angle brackets, we spell out what the policy is. So the first one of these was intended to limit service messages to either hello or goodbye. And the second one is intended to limit tenant messages in the service instance, either world or planet. Just a toy example. Those were validation policies. We also have security policies. So for example, here we have a policy that is designed to limit what users are able to interact with an example service object. And what this says is you can interact with it if you're an admin, or if there is a privilege object that binds your user record with that particular example service. Then we can also extend these model policies to other objects. So for example, we can take the example service instance policy and we can extend it by calling the example services policy using the example service instances owner. And way down here at the bottom is just an example of the syntax that you would use in ExProto to do this. So we've added this : example service policy section that links in the security policy, and this validator option lists the validators as well as the error messages that would be printed if a validator is violated. So we've shown you all of this stuff, but we haven't actually run it yet. It's because most people are going to encounter this run automatically during the core builder phase of the build system. But you can run it manually if you want, and that's going to be demonstrated, I think, in tomorrow's synchronizer discussion. The reasons you'd want to run XOS Gen X manually would be for iterative development or testing. So for example, change something in your ExProto file and observe what changes in the output. Also to generate service stubs. So for example, we can generate entire scaffolding of a service, synchronizer stubs, data model stubs, policies. We can generate all that from ExProto and give you a starting point to get your service started. We do heavily suggest you attend both the synchronizer talk tomorrow if you're interested in this, as well as the hands-on tutorial sessions this week, where you will learn how to deploy a service. So the hands-on tutorial is going to take you through modifying ExProto all the way through bringing up your service in the build system. So I wanted to talk a little bit, the final thing we're going to cover is the XOS SH Tool. This is designed to be an interactive shell that lets you interact with the data model. It connects to the XOS core container via gRPC API. So you actually do use this against a live core. You can run it against a running pod someplace. It's useful for debugging and development. You can use it to inspect a data model, as well as you can modify a data model by creating objects, deleting objects, modifying objects, etc. So you run it from a cord head node. I've given the command here, which don't write it down, just go to the slides and find it there and copy paste it. The one thing you'll have to note is you do need to supply a username and a password, because it does have to authenticate itself to the core. I'm going to do a very short demo of that. So in this window, I am logged in to a Cord in a Box experiment on Cloud Lab. So let's, actually I am not. I think I've lost my internet connection. Okay, so we'll SSH into the head 1 VM. Then I've already set up the command that I would run down here with the appropriate username and password. So when I execute it, it's going in and it's contacting the core. It's downloading the entire schema from the core, so it knows all of the objects in the data model. Takes it a couple seconds to do this, and it's brought up XOS SH. So as it says here, I can do a list objects. This tells me all of the objects that the core knows about. So somewhere in here should be example service instance, embedded image, color should be up in there. Yeah, there's color. So these are all of the models that the core knows about. If I wanted to list models, I could example instance. That is all of the example service objects that have been instantiated. I could get the first one. That's the first one, and then if I do the internet is being kind of slow, .dump. This has shown the contents of that example service instance object. So you can see there's lots more fields than we showed in the talk, because a lot of these were inherited. So these 4 or 5 here are feedback state, all this back end stuff. This shows that it was successfully enacted. If it wasn't successfully enacted, show you when it had run next. So creation timestamp, enacted timestamp. What instance was created in OpenStack. Going down, we should see the name of the object. There's a tenant message was set to goodbye. This is an object I've been messing with before. The class names, this is everything that was inherited for this object. So this was an example service instance. It was also a tenant with container, a service instance, and an XOS base. So I could take this. This is an actual Python interpreter, so we can execute arbitrary Python. I could change the tenant message to hello. And then save it. There's similar ways that I could create objects. I could delete objects. This is kind of a playground for people to use to interact with the data model and experiment. Okay, and to wrap up the talk, we wanted to have some requests for community help. So what can the audience do to contribute back to Chord? And some things that you could do is you could implement new VNFs. One thing that's often talked about is a firewall VNF, something that could be inserted into one of the service chains and would allow the subscriber to configure a firewall to limit the traffic that could reach his home. So that would be an example of a VNF. You could also do support services. So just like ONOS was a support service that other services were able to leverage, like VTN was able to use ONOS. We could propose someone could implement Apache Cassandra as a service, and that could be a new building block that other services could leverage. So we'd really like to grow the inventory of both VNFs and support services, because having those building blocks allows people to implement more complex things without doing as much work themselves, since so much has already been done in the building blocks. The other thing that could really help us out is people who would want to expand the auto-generation use cases. That means writing more XTarget files. So anytime you're implementing a service and you say, boy, this is a bunch of menial work that I'm having to write all of this code, I should be able just to auto-generate this. Look and see if there's an opportunity to write an XTarget for that. In particular, we would love to find some examples where VNF implementation could be influenced by an XTarget. So for example, we have this whole security framework. Could you push that security framework inside of a VNF and use that security framework internally? One of the toy example we've thought about is, let's take example service and generate an HT access file to control who could access the web server that's brought up by an example service. Or just anything to help automate sync step generation or to automate Ansible playbook generation. Anything that can be used to make other developers' lives easier to automatically generate stuff from their ExProto specification would be very helpful to us. Resources, as usual, we're going to point people to guide.openchord.org, where you will find the OpenChord guide. Not listed here is the wiki. That's also a useful community resource, would be the wiki. I imagine you'll have those referenced in most presentations, but go there to learn more about Chord. And I think that's it, and I'm open for questions. All right then, thank you.